Today we're going to go through single and double replacement reactions, which is something that we started talking about last week. But there's a few tools that you have to use in order to figure out if reactions will happen. So that's mostly what we're going to be talking about. So we're going to describe and define single replacement reactions, describe and define double replacement reactions, identify some types of reactions that we see, and then complete the quiz together if we have time. I think instead of doing that, I'm going to give you guys a code word for some bonus points for the quiz. All right, so here's a warm-up question to start off. What do you think a double replacement reaction is? Just thinking about the terms themselves, what those words mean. And based on what we talked about last week, what do you think a double replacement reaction means? Two being replaced. Yeah, Catherine, you're exactly right. It's a pretty simple explanation. Instead of just one thing being switched, both things are being switched. So ions of two substances change places in a solution. Now, last week we talked a little bit about aqueous, right? The prefix AQ and how that represents ions dissolved in a solution, right? So in this case, that's what I'm referencing when I say ions in a solution. It's an aqueous solution. This box here is straight from Canvas, right? This is literally what it looks like in terms of letters. You start with a Y plus BZ, and the Z and the Y switch places. Pretty self-explanatory. Honestly, double replacement reactions are the easiest ones to see because you start out with two substances and you end up with two substances and they have just switched places. Now, the easy thing about it as well is that these are ions, right? So the positive ion and the negative ion will go together. So it's also really obvious which ones switch if you're looking at the charge of the ion. So some examples of this, just to really get into this even more. So notice I don't have my subscripts written here. I'm writing this the same way that you guys can write when you turn things into Canvas. You can place your coefficients in front, and you can even use your subscripts. You can keep them as big numbers, and I'll understand what that is. Right? If you want to take the time to make them into subscripts, you can. But really what you're looking at here is this is an NO3. The 3 is here, right? And then there are actually also 3 of those ions in this situation. So also recall that OH, right, one of those polyatomic ions, as well as nitrate here, NO3, those are going to be our negative ions, and basically in our final products here, they just switch places. Same thing with this example down here. A really similar example, right? We have an OH ion and we have an NO3 ion, and again, they switch places. So this is a helpful place for you to look at your polyatomic ions chart so that you would know what the charge is, or you can figure out what the charge is, right? We know aluminum would have a charge of +3. So our nitrate here, we have 3 of them. That must mean that one has a charge of -1. So NO3 as a polyatomic ion is a -1 charge, but in this case, we have 3 of them, right, to help balance out that aluminum. Whereas OH and sodium, our hydroxide, we know, has a -1 charge, and sodium has a +1 charge, right? So those two just happen to pair up super easily here. So don't be afraid to look up the charges of some of these ions, right? And again, recognizing which part is the ion can be difficult because you may not recognize NO3 as an ion, right? But it is an ion. So have that chart handy when you're looking at reactions, especially when you're trying to figure out which type you're looking at. So just another final little thing on the double replacement reactions, because then, or a couple more things actually, then we'll move on to single replacement, which sounds like it would be easier, but is actually a little more complicated. So a lot of times in a double replacement reaction, or generally in any reaction, you'll end up seeing the formation of a solid, right? And we call that a precipitate. And why it's called a precipitate is because it literally will fall out of the solution. So for example, here you have two compounds that are in aqueous solutions, right? Meaning they're dissolved in water. So they're ions floating around. When you combine them together, you get a solid, right? And you will see that. You'll mix two liquids and you'll see a solid actually come out, right? Precipitate out of the solution. So sometimes you will see the prediction of a solid. And there are solubility rules that will help you predict this. For the most part in this class, a lot of this stuff will be kind of given to you, but I want you to notice, right, that that's a thing. Sometimes solids will form. Sometimes, we'll look at the next slide, gases will form, right, as a product. Again, these are signs that chemical reactions took place, right? A lot of people learn those early on in basic science classes, right? If there's a gas formed, if there's a solid form, if it gets hotter, if it changes color, right? A lot of those are signs of chemical reactions. Well, here we're seeing it written in the chemical formula. So also formation of gas bubbles, again, something that might happen from a double replacement reaction, where in this case, right, we start out with two solutions that are aqueous, again, dissolved in water, and when they are put together, we end up getting a gas released instead of a solid. Okay. So we talked about this a little bit last time, but I just want to emphasize it again because acid-base reactions are technically double replacement reactions, right? Because the ions are switching places. However, you always get the same products. You always get a salt and a water. So the reaction that we looked at last week was actually more complicated than this. But really, again, you want to think about what your ions would be because we're in an aqueous solution, which means these are dissolved in water. We would have a hydrogen ion, which would just have a positive charge. And we would have a chlorine ion, which would just have a negative charge. Type a 1 in the chat if you feel really confident about identifying the charge of ions. Type a 2 in the chat if you would like for me to explain how I find out the charge of the ion. So 1 in the chat, I'm good on figuring that out. 2, I would like to know how you figure that out. Okay, so Oliver said, we're gonna address right now, same for Aiden. So, okay, so some of this comes from the periodic table and some of this comes from your polyatomic ions. So the first thing is periodic table is going to be for elements that are located by themselves. So for example, hydrogen and chlorine, right, together they make hydrochloric acid. However, they are separate. There's no polyatomic ions there. So you would look on your periodic table and you can actually use a trend, sort of, I guess we'll call it a trend, to figure out the charge. So everything in group 1 will have a charge of what? Catherine might know this. I just told you the answer for hydrogen, and guess what? It's the same for all of group 1. Well, let's think about it. So we know that group 1 has 1 valence electron. If an element has 1 valence electron, that means they need 7, or in hydrogen's case, 1, to fill their shell. What are the chances that one of those elements is going to gain 7 electrons? Pretty much 0, right? That's not happening. So all of the elements in group 1 will donate an electron, which will leave them with a positive 1 charge, right? Because they're losing a negative. So everyone in group 1 will have a +1 charge. Group 2, same concept, will have a +2 charge. Why? Because they have 2 valence electrons. Again, they need 6 electrons. They're not getting 6, right? So they're going to donate 2 electrons, lose 2 electrons, and then have a positive charge. Everyone in group 3, right? Because remember, metals we skip over. They have their own fancy rules, and those are actually easy because they'll tell you in the name. It'll be lead 4, copper 2, silver 1, and it'll tell you what the charge or the valence electrons are for your metals. But group 3 over here, with being led by our boron, will be a +3 charge, again for the same reason. 3 valence electrons, still more likely to give up to 3 electrons than to get 5. Now, group 4 is where it's interesting because this group is pretty much not involved in forming ions. -10, but 10 is a metal, and so it sort of follows its own special rules. But group 4, for the most part, we don't ever see. Like carbon would never become an ion by itself. Same with silicon, same with all the rest in that group. Lead and tin, you will see doing stuff, but they're going to kind of follow with metals in this case. They're not going to follow group 4's rules. Once you get past group 4, this is where we start seeing negative ions. So for example, here in group 5, we have 5 valence electrons. Well, they're not going to give up 5 electrons. They're more likely to get 3 electrons. So our nitrogen group will have a charge of -3 because they will gain 3 electrons, giving them a negative charge. Oxygen's group will have a charge of -2 for the same reason. 2 electrons will be gained to complete the valence shell. And then finally, our halogens will have a charge of -1 for that same reason. They have 7 valence electrons. They just need 1 in order to have a full shell. And if they gain an electron, they will have a charge of -1. Noble gases, again, don't usually react, so we don't have to worry about them becoming ions. So it's pretty easy. It's 1, 2, 3, and then -3, -2, -1, with carbon being the middle, right, of that pyramid. So again, I explained the valence concept here because that's where these charges come from, right? They're not just made up. They are determined because of the valence and whether the electrons will be gained or lost. Now, that's how you can figure out something like hydrogen and chlorine. What about a polyatomic ion, right? Do you need to memorize those? Of course not, because there's a bunch of them, but you should definitely have a polyatomic ion chart. I know I included one in a previous virtual session, but just in case you don't have one or you lost that one already, you can actually just look one up. I always just go to images for this, right? And you could pick any of these. They're probably, this is the one I think that I might have included in our chart, but this doesn't include all of them. So you might want to pick a more expansive one for your notes. But this will tell you the charge of a polyatomic ion, which again is a group of elements that stays together and becomes an ion. So hydroxide, or OH, right, is a very common one. It has a charge of -1. Some of these other ones you'll see with the 2 or the -2, those mean that they have a charge of -2 or -3, right? It's common notation to actually write the number first. If you see any numbers that look like exponents, right? An exponent type number is actually telling you about the charge of that group or ion. Yeah, so definitely have one of these because that's how you're going to know the polyatomic ion charges. However, you can also figure that out just by looking at what's happening in the formula, right? So for example, let's say that we didn't know the charge of hydroxide, or OH. Well, if we know the charge of sodium and they're bonded and they don't have any subscripts, we know that they must have a 1-to-1 ratio, right? So sodium is in group 1. We know that sodium has a charge of +1. So hydroxide must have a charge of -1, right? Again, you could look it up. I'm going to put parentheses around it so that we know it's an ion, right? Again, our hydrogen has a charge of +1, chlorine -1. So this one's really easy because everything has a charge of 1 or -1, so they can all shift positions, and you don't even have to worry about balancing this equation or figuring anything out. So in this example, the double replacement is that the chlorine replaces OH and OH replaces chlorine, right? Which gives us water and sodium chloride. In this case, it's dissolved in water, right? But if we evaporated the water, it would be salt. So keep in mind, when you have an acid and a base, you're always going to get a salt and water. If you're not sure if it's an acid or a base, try to see if a double replacement reaction would work, right? In terms of charges, in terms of does everything able to switch places? And you might notice that you'll get water a lot of times. Maybe it was an acid base and you didn't realize. You can always refer to our last virtual session for some tips on how to identify acids and bases just from looking at the formula. Okay. Single replacement reactions. So these are, Bella, welcome. These are actually easy to see, right? Like if you look at it, you can say this is single replacement. However, here is the tricky thing. These do not always happen. An acceptable answer for these, and an answer that you will see actually on some quizzes, is no reaction takes place. So you have to, first of all, recognize that it's a single replacement reaction, and then second of all, determine if the reaction will happen. Okay, so let's start breaking this down. All of these single replacement reactions will involve metals. Lithium. There will always be a metal by itself, right? Because it's single replacement. If this metal was bonded with something else, it would be double replacement. We'll always have another compound that also has a metal. Zinc, looking like a metal. What will happen if the reaction works is that the lithium will replace the zinc, right? And zinc will be left by itself. Seems pretty easy. Now, we know though that not all metals are as reactive as other metals, right? There's rules for this. So we use something called an activity series, which again, add this to your notes. There's a bunch of versions of this. Some of them are, more extensive than others, but you need to use the activity series for single replacement reactions. You absolutely have to. And all you do is look at it and it kind of tells you the answer, right? So decreasing activity. Metals, and in some cases halogens, because they can do this too. Usually you'll see metals though. Some metals are more reactive than others. So lithium is the most reactive metal. It will replace anything. Potassium will replace anything except lithium, right? Calcium will replace anything except potassium and lithium, and so on. So gold is not very reactive. If you had gold sitting by itself, it's most likely not going to do anything. So in this case, checking out our first example here, right? Well, we see AU. What does AU stand for? Which element is that? It's gold. Imagine that I gave you a gold example, right? So gold is pretty low on our activity series. But we still check, which metal is gold attempting to replace? Well, it's attempting to replace zinc. So I find zinc on my activity series. Zinc is pretty high up here. Gold is never going to replace zinc. So in this case, if you mix gold with zinc chloride, you get no reaction. Nothing will happen. If we do it the other way, so we have zinc and we combine it with gold chloride, well, guess what? Zinc is higher up than gold on the activity series. Zinc will replace gold. So in this case, it does matter which metal is by itself. So when you look at the activity series, you ask yourself, okay, is that metal strong enough basically to replace the other metal? And the answer might be no reaction. It's a possibility. In fact, if it is no reaction, then your work is much easier, right? Because you just write no reaction. Now notice hydrogen is on here, right? Is hydrogen a metal? No, right? But it does behave like a group 1 metal does. So sometimes you will see hydrogen involved in this. Halogens can also do this. Again, not as common as metals. So most single replacement reactions involve metals, and you just have to look and see, basically, is it strong enough to replace the other one? So let's try. I have too many things open. Okay. Okay, so here's another activity series, then we'll try. This one is the one I took straight from Canvas. This is a little bit more detailed in terms of what happens and includes more metals than the first one, right? I like this first one better just because I think it's easier to see and identify. But make sure that you know all of the metals and all of the potentials here. So I would have this available for when you take the quiz because they will ask questions based on this chart. Yeah, so here it gives you a little bit more like explanation, right? Replaces less active metals, replaces H's and acids, replaces an H and H2O, etc., right? Where it'll give you a little bit more detail about what those metals will actually do. So now let's try. Okay, so predict the products. This is basically what your life is going to be like in this class for the next few weeks. Predicting products from reactions. And there's two ways you can do this. You can take the cheating shortcut way of looking it up, right? Try not to do that. The purpose of this is that you learn and understand what's happening in these reactions by predicting them. Now, if you try to predict and you can't figure it out, then look it up and then figure out how to explain it that way, right? But don't be tempted to just Google it, right? I know it's tempting, but there's no way really for me to know that you did that, except once we start getting into more complicated stuff. If you can't understand what we're doing, it's probably because you didn't do this pre-work, right? This is pre-work, essentially. Understanding what is happening in the reaction. It's important. It's an important component of the class. So, predict the products. We'll do the first one together. Then you guys will try to do the other ones and we'll check. So first one, we have zinc and hydrochloric acid. Well, we want to know, will this react? We check our activity series. Zinc is higher up than hydrogen. So yes, this would happen, right? We would end up getting zinc chloride plus hydrogen. Now, is that all you have to do when you're predicting the products in a reaction? What should I do to make sure that this is correct? There's two things. Combine them? Well, they can't combine anymore, right? Because it's a single replacement, so they did switch spots. Well, I need to check to make sure that my charges are balanced. And then I need to balance my equation. So, zinc and chloride. Well, what would the charge be for zinc? We need to check our periodic table potentially, right? In fact, I have one. I'm going to move around here. I have a giant one in this room that I'm just going to look at. If you have a periodic table, take a look at it yourself. Where is zinc? Let's see, where are you, zinc? Why am I? Oh, there you are. Zinc is number 30. Okay. So zinc is one of those weird metals where maybe we don't know the charge of it, right? Because it doesn't fall into any of our regular groups. I'm pretty sure it has a charge of +1, but in this case, I would Google it to make sure. So, oh, come on, zoom. There we go. So I would say zinc charge. Zinc has a +2 charge. Thank you, Logan. Right now, if zinc had multiple options, like it could be +1 or +3 or something else, right, then you probably couldn't predict further than what we already did. But in this case, zinc only has one option for a charge, and it's +2. So going back to our equation, what does that mean for us, right? Do we care about that? Well, we do. If zinc has a charge of +2, would it just combine with one chlorine? Oops. No, right? Because we're going to have zinc that has a charge of +2. And we have, which by the way, my Z kind of looks like a 2, but it's a zinc. And we have our chlorine, which has a charge of -1. So in this case, we would actually have zinc chloride. We would have 2 chlorides to make that a balanced molecule. Now, hydrogen, we just leave, right? Most likely hydrogen would combine with itself, but we'll just leave it like that. Then we have to balance our equation, right? We balanced our product. Now we have to balance our equation. Well, we have 2 chlorines on this side and only 1 over here. So we're going to need to put a 2 in front, right? We're going to need 2 molecules of hydrochloric acid for every molecule of zinc. And then we're going to have to place a 2 in front of our hydrogen as well, because now we will get 2 hydrogens and 2 chlorines on each side. Right? So predicting the products involves multiple steps. First of all, figuring out what kind of reaction it is, what's going to happen. Then you have to make sure your charges are balanced. Does your molecule make sense? How would those things bond? Then you have to balance the overall equation. Right? So this is kind of combining a lot of the stuff that we've done in the class into one process. Okay. You guys tell me, do you want me to do number 2 with you as an example? Or do you want to try number 2 by yourself and then we'll go over it? You can just type like you or by myself or something like that in the chat to let me know. Okay, most people say try it. Bella says you. So we'll go over it. So I want you guys to try, right? Look at number 2. At the very least, use the activity series to figure out if this reaction would happen, right? Then try to work on your charges and your balancing, and then we'll go over that. If you finish 2, try 3. And then we will go over those as well. And you may need, for number 2, this much bigger chart. Which I don't know if I want to flip back and forth between these things for you guys, but barium is not on this chart because it's a pretty infrequently used metal, but in this case it's used. So write your reaction, Mg plus barium chloride, right? And then you're going to need to use this activity series. All right, so does anyone have an idea yet what our products would be at the very least, even if it's not balanced or whatever? Would this reaction happen? Okay, so Logan is suggesting something. Well, that's an interesting suggestion, Logan, but remember, in a single replacement reaction, metal will replace metal. So chlorine will never be left by itself. So first, let's identify our metals. We have magnesium and we have barium. Now, barium's not on this list, right? So I need a bigger activity series to be able to answer this one. If I come back here, I locate my two metals on my activity series chart, Ba and Mg. Well, magnesium is lower than barium. So will magnesium replace barium? It won't. So in this case, the answer is no reaction. Magnesium is not a strong enough metal to replace barium. So nothing would happen there. If something did happen, we would get barium plus magnesium chloride, right? But it wouldn't happen because magnesium is not a strong enough metal. So again, how did I figure that out? I identified my two metals. I checked my activity series to see if they would replace, right? Metals on the top are the strongest, metals on the bottom are the weakest. Okay, so let's try the next one. No reaction, which will become probably your favorite answer. Oops, I didn't mean to erase that. Okay, no reaction. So then what about the next one? Copper chloride plus plus sulfuric acid. What is going to happen here? I'm going to give you a few moments to look at this one. And let's start with the basic question here. What are our two metals for number 3? Which two metals are we looking at? Well, one of them is not really a metal, I will say. Copper and hydrogen, good. So copper is a pretty easy metal. You're like, okay, got that one, right? The other one you go, well, that's not a metal, but hydrogen, it counts because it does actually interact in this situation. So in this case, we have copper, we have hydrogen. So we want to know, will that copper replace the hydrogen? So we come over to our activity series, we see copper, we see hydrogen. Well, will copper replace hydrogen? You guys tell me. No, you're right, it won't, right? Copper is less reactive than hydrogen. So again, this one would be no reaction. Again, because copper is lower than hydrogen, copper will never replace hydrogen. Okay. What about the next one? Which two metals do we see? Thank you, Catherine. We see calcium. Oops. And we see potassium. So calcium is one of our metals. Potassium is our other metal, excuse me. I'm getting tired. All right, so we want to know, will calcium replace potassium? Let's take a look at our activity series. Potassium, calcium. Will calcium replace potassium? It will. Now, these two examples for 3 and 4 are a little more complicated because you'll notice the metal's not by itself. What's actually happening is the metal compound is reacting with an acid. So these are sort of like advanced versions of this. Again, this is a supplement to the lesson for this. So if you go through the lesson after this virtual session, it's going to really click for you. But regardless, right, calcium will replace potassium, because I know some of you out there are probably thinking, well, how come on number 3, hydrogen couldn't replace copper, right? Because it could go the other way, maybe you're thinking. Well, in this case, it doesn't work that way. It's going to replace something in the acid, right? Again, you will learn a little bit more about that process from the lesson. I want to work on the actual balancing equation ion kind of stuff here with you guys. So we have calcium, we have potassium. We know calcium will replace potassium. So now let's talk about our ions. What is our charge for a calcium ion? Well, calcium is in group 2. Calcium will be a +2 charge. Chlorine, right, we already know, we're very familiar. It's a -1 charge. Notice there are 2 chlorines for 1 calcium, right, because that's going to have them bond. Potassium, on the other hand, is a group 1 metal, I believe. Let me double check that. Yes. No, it's a group 2 metal. Just kidding. So its charge will be plus. Nope, it's a group 1. I was right. See, even I don't have the periodic table memorized 100%. It will be a +1 charge, right? And then our other ion here is CO3, which is a polyatomic ion. We could look on our polyatomic ion chart, or we could figure out the charge just from looking at the bonding here. We see 2 potassiums for 1 polyatomic ion here, right? I believe it's carbonate. So we know that this must have a charge of -2. Okay, so knowing that, what would our products be? We know the reaction will happen. It is carbonate. Whew, okay, good. Losing my mind here. Too many chemicals. Okay, so you are exactly right, Catherine. We would end up getting potassium chloride plus calcium carbonate. And they're already balanced, essentially, right? At least the molecules are, because potassium has a charge of +1, chlorine has a charge of -1, so those will bond without any subscripts. Same here. Now, you're right. Now we just have to balance the equation. I'm glad Catherine is with me here. Hopefully the rest of you guys are following this. So how do we do that? Well, we look at our left side first. I see 2 potassiums and 2 chlorines. So guess what? I just have to put a 2 right in front of my potassium chloride, and it's balanced. Okay. Last and final example. Sodium and magnesium chloride. First question you should ask yourself, will this reaction happen? What are our 2 metals? Catherine says no. Well, let's confirm. We have sodium, we have magnesium. Let's come to our activity series. There's sodium, there's magnesium. Will sodium replace magnesium? Catherine says no. What do the rest of you guys think? It will, right? Because sodium is higher up, just by 1. So sodium will replace magnesium. So this reaction will happen. Okay, so it's going to happen. Well, no, that's okay. If you, like I said, if you were looking at it the other way, you would say no, right? That's why it's very important that you get which metal is trying to replace which metal correct. Right? Which when it's by itself, it's a little easier, but it can still be confusing. So what would we end up getting? we know sodium's going to take the place of magnesium, so we're going to have NaCl plus our magnesium will now be by itself. Again, we want to think about charges. Sodium has a charge of +1 because it's in group 1. Chlorine has a charge of -1 because it's in group 7, right? And magnesium has a charge of +2, but we don't really care about that because it's by itself over there. So the sodium chloride itself is bonded correctly, but then now what would we need to do to balance our equation? Is it balanced? It's okay, Vitaly, you can watch the recording because we're about to finish here, and then you can watch the recording of the whole thing. Subscript, we actually need, it's called a coefficient. So when you're balancing an equation, those numbers that you're putting in front of things, those are called coefficients, right? It's confusing. So that's actually a good point. Let's talk about what those things are called. So let's say we have, actually that will be a bad example because that's not what I wanted to show. Let's say we have MgCl2. You'll have to understand with my terrible art. Okay. So MgCl2, this number here, this is a subscript. This is telling you how many chlorines there are. Subscripts are when you do bonding. So your subscripts will tell you how many of each element you need to bond. Right, in this case, sodium chloride, we only need 1 of each. So we don't have any subscripts, right? Because you don't need to put a 1, that's implied. Here, right, in H2S, we know we have 2 hydrogens for 1 sulfur, and that is necessary for them to bond because sulfur has a -2 charge and hydrogen has a +1 charge. How else are they going to bond if they are not getting 2 hydrogens for every sulfur? Now, once you've made your molecules, right, and they've bonded correctly, then the number that you put in front, let's say we put a 4 here, right? This would not be correct for our equation, but we'll go with it. This is called your coefficient. This is for balancing your equation. So that's telling you how many magnesium chlorides you need for this reaction. So most of the time you're not going to need to say subscript or coefficient necessarily. You're just going to be drawing them or writing them. It does get confusing though because you will see sometimes things are just written straight across, right? And it's not written as a subscript versus as a coefficient. But there is a difference between the two. Subscripts you figure out first, then you do coefficients. Once your subscripts are figured out from your bonding, you don't change those, right? I would never change this 3 because this is telling me there are 3 oxygens part of that carbonate molecule. I can't change those, otherwise I change the entire compound. What I can do though is change the coefficient, which would tell me how many of those carbonate molecules there are. Okay. So subscripts are for bonding, coefficients are for your balancing of equations. So do we need any coefficients for number 5 here? Is there something that's unbalanced? Yeah. What is it? I see 2 of something on the left side and 1 of it on the right side. What molecule here or element is unbalanced? Chlorine, right? We've got 2 chlorines on the right or the left side, and I just see 1 chlorine here. So to fix that, we can put a 2 in front of our sodium chloride, and then we can put a 2 in front of our sodium. Now we have 2 sodiums on each side, 2 chlorines on each side, 1 magnesium on each side. Okay, that was a lot. Thank you guys for staying in there. Hopefully this helped you a little bit. Again, this is getting into the harder part of this class, right? Predicting products, incredibly hard. And then once we've done that, we're going to start actually figuring out how many moles of each thing you need, right? And determining which reactant is the limiting reactant. So all of the stuff we've been learning is just going to keep coming back. So if there's anything you're confused on, please ask me, right? Especially because you're probably not the only person who's confused. And I'm happy to create that topic in the virtual session so that you can go over it with your peers here. Okay, so again, most of the time you see one metal replacing another metal. One metal is usually by itself. However, there are situations where you have acids and metals replace metals in acids. Read the lesson to get a little bit more background on that and a little bit more examples. You need the activity series, right? You have to use this to predict. If the metal's on closer to the top, it will replace. If it's close to the bottom, it won't, right? So look at where they are on the activity series, figure out if the reaction would even happen. If it does happen, figure out how the bonding would occur, then figure out how to balance your equation, right? So it's a lot of steps. Okay. So there is a code word for today, and the code word is typed into the chat box right now. You can use that code word to get 3 bonus points on this specific quiz, right? Which I think it's called single, it might be single and double replacement reactions. It might just be single replacement reactions. Now that I think about it, I can't remember exactly what it's called, but we will look at it right now in Canvas. And then I will let you guys go. Does anyone have any questions about anything that we covered today? Because that was a lot of stuff that we just talked about. Or do you have any suggestions for next time? Something that you would like for me either to go over again or go over for the first time? Okay, Catherine says, I'm ahead. Yes, so if you've already done the quiz, you can certainly add it as a comment and get your points for sure. Let's see, the quiz is called, it's called Double and Single Replacement Reactions, right? It is due on December 6th, which is in a few days. So you should have plenty of time to go through the lesson. You could rewatch this video. I'll post the recording tomorrow and hear me go over the content again if you need. And again, email me, right? Even if you're mid-quiz and you're like, what is this question? Send me an email and I'll try to answer you as quickly as possible. But if you've already turned in your quiz, we can talk about getting some points added back if if your question would have helped you get it right. Okay, so again, as you're going through this stuff, guys, let me know what's confusing to you. So if you're like, what's the difference between a coefficient and the subscript? What's the difference between this? How did you find out the ions, right? Ask me these questions, and then I can explain how to do them. We only meet once a week, so it's hard to cover all the stuff that I want to cover. Okay, otherwise, make sure you've got the code word written down, and I will see you guys next week.